Okay guys, so we finally got it working. Not too sure what was going on, but it's finally working. So we managed to pass the training data JSON and actually display it in the console. So you can see it's an array of 750,000 terms. So you can expect why it was so laggy, but we can just have a look at one of them. So we have the expected outputs 1,0,0,0. So that means that this is going to be an addition sum, and this is the input. So this is basically coded in an addition sum. You can't actually understand it because it's in binary, but this has all the information of an addition sum coded inside of it. So that's what's important. If we look at another one, this is 0, 1, 0, 0. So this is subtraction, and again this is going to have a subtraction sum coded inside of it. So yeah, it would actually be nice if we could convert this back, and we actually can because this is in binary. So in the future I might create a function to convert back just so we can see which ones is actually happening, but for now this is what's important. So we've got the input and we've got the output, and it's actually quite fast now, so this is good. It still takes a while, but yeah, it's not too bad, it's not too laggy, so this is good. Now what I'm going to do is I'm actually going to start training data. So I'm going to import this neural network, and I've already imported the scripts, so now I can just follow the instructions on this. So we need to initialize our network. Let's copy this, and I'm just going to make a lot of space just so we can actually see it. So yeah, let's initialize our network. First of all, we have our network, and this is actually just a list of layers, but that's not too important. We don't need to understand how the inner workings of a neural network work for now, because we just want to try and train this data. So this data is I actually think I wrote down the size of it somewhere here. Okay, well I know each length of each input is going to be of 42. Actually, I can just work that out. You can just say dot inputs dot length. We can just see this, and yeah, okay, so each input array is of length 42. So our first layer needs to have 42 neurons in it for each input. And if we look at the expected outputs, we actually have, yeah, so the length of the expected output is 4. So the output layer needs to have 4 neurons, which leaves us with just these it leaves us with these hidden layers inside. Now I know this is already a pretty large network with 42 input layers, especially for this library in JavaScript. It's going to be really slow, so probably going to start off with only one hidden layer, and we need to make this decently sized. So I'm probably going to make it 15 neurons so that it's got some good width, but it's also not too big that it's going to take really long to run through the network. So now we've done that, we can move on to the next step. Let's just make a free gap. So next step is we need to get the data, and we've already got that here, so that's good. Now let's just take out this entire thing. So I'm just going to copy this, let's just copy it like that, and we'll just train it like so. So yeah, you can see how easy it is to use this library. I'm just going to take this, and we just need to change around these cycles a little bit. So epoch cycles, that basically means how many times we're going to loop through the entire data. This data is huge, so I'm going to just leave it start at 1, and step size we'll just leave that at 0.01 for now. And yeah, mini batch size, so this is also important. Since this is such huge training data, we definitely want to split this into mini batches. So I'm probably going to start very small with a mini batch of 100. That would be fine. And yeah, okay. So now what I'm going to do is I'm actually going to get a callback. Let's see how you do that. Yeah, okay. So we're just going to see, just to get a rough idea of how slow this network is. We'll calculate the cost as we finish epoch as well. So, like so. Okay. This is pretty much all we need. now we can actually start. I think I've just saved this, and yeah, okay, so let's go. Let's see the general speed of this, and so now I've only got the first 20,000, we should be getting much faster performance. So I'll try this again. I'll probably like speed through all the other stuff because I know it was a bit of a waste. So I'll just probably speed up the rest. But so we've got nice and fast training data. Let's now start to train like so, and we actually should see some good improvement now, I hope. Okay, so I've reduced the training data even smaller because I was just getting a little bit annoyed at how slow it was. But yeah, so you can see we are getting pretty low costs of 0.02, so we're approaching that lower than 0.01 boundary which I'm looking for. The only problem is, since I've reduced the training data so low, I don't know if it's just memorizing these answers, if that makes sense. So we'll have to see by switching up the training data and just using a completely different range. But yeah, for now it's looking good, so I'm just going to let this run until we get to below 0.01, which is not looking too promising right now because it seems to be getting stuck at around this 0.16 value. So I might have to decrease the step size just a little bit to possibly get it out of this loop. Okay, so you can see it's really struggling to get lower than 0.01. It's really just getting stuck now at 0.1014, which is better than 0.016, but we're still 0.004 off of our target. So at this point I might try to, if I decrease step size anymore, it's just going to slow down even further, which is not good. So I think we might just have to accept this low thing. The thing I'm more interested in though is seeing if this is really just because it's memorized the answers, because 0.014 is still pretty good, like it's still a pretty good cost. But I'm interested to see if it's just memorized these answers in the first 1,000 entries of a training data, or if it's actually learn how to identify an operator. So to identify that, we can just use a different range, which is just going to be completely new training data. So that way we will know if it's identified the operator. Okay, so we're here, and I'm just going to pick a completely different range. Let's say we want the training data from, let's say, I don't know, 300,000 to 301,000, like so. So this is completely new training data, and let's just see how well it trains on this. We could just see the cost. Actually, we'll just train it on this just to get an idea. So let's just reload this and have a look. Okay, so yeah, so we're actually still at 0.04, which isn't great. So that does tell me that it was just memorizing answers, but it's still not too bad, like 0.04. So we'll say this is for specific range, and we'll say 0.04 for a random sample, almost like we're testing it, but not really. But yeah, so I think what we can do is, if we just keep on cycling these ranges, eventually it'll get used to it and it should just work everywhere, if that makes sense. So we'll just train it on a bunch of different ranges, and yeah, I'll come back to you with the results. Alright guys, so as you can see, we've actually managed to get the cost really low to 0.005 on this specific training data, which I just left it on, 250,000 to 255,000. That was pretty good. I haven't actually tried on any other training data, so yeah, let's actually test it now on a different training set. Let's do something like, let's actually go to the far end, so we'll do 700,000 to 700, and let's just do 700,500 because this is just to test it. I'm hoping that we see some good improvements. So last time we had a random sample cost of about 0.04. Alright, so let's see if this is going to work. Ooh, okay, this is actually really interesting. So we get the cost of 0.05 again. Okay, this is actually really interesting. So I'm seeing that we're getting now a cost of 0.05 for a random sample, which is great, and it's reducing really quickly. So, that's super interesting. I do want to calculate the cost, but I really don't know how long it's going to take. So, okay, let's just, since we're actually changing the training data itself, this shouldn't take too long. So this is just the cost for this range of inputs. Now let's just reload this, see what it gives us. But yeah, that's really interesting how even on a random set of data we were able to get a cost of 0.05. That's really good. Range, see the average cost for this range, 0. What? That's okay. And yeah, let's just start expanding the range. So I'll put it to 675,000. So yeah, we're gonna get the majority of unknown samples here. And okay, so we get 0.09. Okay, it's still pretty good. It's still below 0.01. Sorry, 0.009. But yeah, it's still below 0.01, which is good, although we are definitely seeing increases in cost. So, you know, that's to be expected, I guess. Yeah, let's try now just 600,000. We get an average cost of 0.01. So it's not below 0.01, but at the same time it is basically right on it. So it's not too bad. Although this also includes the range of that had the 0.03. So yeah, that could be explaining it. I think we should pick a range which have not trained at all. So I remember this is going to be something like the 500,000 to 600,000 range. I've not trained a network on any of this data, so this is fresh data to the network. Okay, so we get another cost of 0.01. That's actually really good. So what that tells me is that the average cost over the whole network is just 0.01. There we go. Okay, so when you put in 0.1, you can see the first one is pretty much 1, so that's pretty certain, and all the others are all effectively 0, so that's really good. So the first one was a success because it identified that it was a 1. Remember that this represents addition, this represents subtraction, this represents multiplication, this represents division. So by putting this as 1, it's been really confident that this is an addition sum, and it is, so that's good. Let's try another number. Let's try something like 9,812. Even though this wouldn't have actually been part of a training data, it may still be able to identify it. Although now it is slightly less confident between addition and division. It still did identify addition as a major, but division was a lot closer. So yeah, we still have a few errors, but hopefully that's alright. Now let's try something else. Let's try something like 881 multiplied by 24. Let's have that one. Okay, so yeah, this was a multiplication sum, and you can see it has effectively identified multiplication, since all the others, you can see these e's to the minus 10. These basically mean that it's really small, because it's just saying it's 10 to the power of minus 18, which is a tiny number. So yeah, you can see this has really confidently identified multiplication, which is great. So that's good. Let's try something else. Actually, let's see what happens if we go over the limit. Actually, yeah, we'll try that. This is probably going to make the network break because it hasn't been trained on this data. And oh yeah, okay, it literally made it break because the input range was too long. Okay, let's try some more operators. Let's try a divide operator. We'll do 764 divided by 3. You can see, yeah, it's really confidently identified division. So this is working really well. Like, this network is actually working a lot better than I thought it was going to work. So that's great. It's important we keep this weight and bias data, so I'll just leave it in the local storage. It should be safe there. But yeah, so we were able to train this network. Although it was really slow, we were able to eventually do it by literally just training data was too long, so we just cut out a bit of training data and train a network on that, and we just did that, repeated that until we got to different points. Let's do one more. Let's try subtraction, and let's do let's just do 42 minus 42. We just reload it. You can see we get equal, and oh, okay. Yeah, oh, okay, I thought we had an error, but yeah, I was just looking at the wrong one. So yeah, again, it's really confidently identified as subtraction. So this is good, this is really good. And we're in a good position to now move on to the next part, which is going to be training a network on actually adding numbers. So I'm not sure whether we will do it as using 4 different networks for each operation, or if we will just do one network but try and give the operation some extra weighting. I'm not sure, but I'll think about it and come back next video. So in this video, all we did was we trained a network on the training data which we'd created previously. So now I can identify the operators within a question. Obviously, this isn't looking too impressive now, but because we've given them in a separate. But I'll show you how powerful this is if I were to just edit the question right here. Let's just say let question is equal to, so now we can put in any question we want. We can put in like 76 divided by 90, and of course we do need to add in the zeros, so we can just add them in at the front. Doesn't really matter too much. So yeah, so we can add them in like this. You can see we just typed in a random string, and the network is able to identify confidently what operator it's been using. So you can see when we put this in, it's able to confidently identify that it was division that's been used. So that's really good. Yeah. So what I think I'll do is, although I've been training a network to put random weighting on either side, what I'm actually going to do is probably just add zeros to the start, because that's what's easiest to do. But yeah, thanks for watching. In this video we trained the neural network on the data which you created previously. See you guys in a future tutorial.